Hi, my name is Ana Cecilia Valdez, and this is lab number 4 for Physics 2211 on oscillations. For this, what we want is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Our purpose is to compare the predicted motion given by glow script with the experimental motion analyzed in tracker. Also, we want to analyze the changes of the energy of the system. The findings for this lab were that the predicted and the observed motion resulted quite similar and that the change in total energy was equal to zero. For the purpose of this lab, we will consider our system to be the mass, earth, and the spring, and nothing as our surroundings. And well, just a reminder on how the forces that we will be working with work. The force of spring acts parallel to the spring and in the opposite direction of the L hat, and the force of gravity acts downward. As you can see in the images, when L is greater than 0, the spring is stretched, and when it is less than, it is compressed. For this lab, we use the momentum principle, which is just F net is equal to mass times acceleration, or just changing momentum over changing time. We also use the velocity and the position update formulas, and we consider the oscillation with the spring force equation, which is the negative k times the length of the spring minus L naught times L hat. We also use different forms of the energy principle. As you can see here, we have kinetic energy, energy due to gravitation, spring, and how the energy of the system is equal to the work of the surroundings, and of course we cannot forget about the force of gravity. Here you can see the video from that we analyzed from tracker, where the mass is released from rest and is constant. We have a mass of approximately 0.402 kilograms, and well, for our predicted motion, to initialize the conditions, we begin by stating a mass of 0.402 kilograms, and our position will be the same as the one indicated by the experimental data from tracker. And well, also since the object starts at rest, the velocity is equal to 0. Then we declare our acceleration due to gravity to be 9.8 meters per second squared, and we proceed to calculate k, which is the stiffness of the spring, by using the following formula where t is the period in the y direction, and while the formula is just this one, k is equal to 4 pi squared over the mass and the period squared. And well, we calculate L naught by deriving that the magnitude of the length of the spring minus the mass times the acceleration due to gravity and the previously calculated k. So that's how we get the L naught, and we calculate the update of the different variables afterwards, and we just uh, put the previously analyzed formulas for kinetic energy, for gravitational potential energy, for spring potential energy, and for total energy, which we reviewed in the previous slide. Here you can see that we proceed by calculating the force of gravity vector, and since we know that gravity just acts in the y direction, the only component that is affected is the y component. The force of the spring is then calculated with the k we got just a second ago, and our net force vector would be these two forces added together. We then update our ball's position and velocity and the spring, and finally we use the different forms of the energy principle to calculate the changes of energy through changes of internal and kinetic energy. So these are energy graph, and as you can see, the change in kinetic energy is much less than the change in potential energy due to gravity and due to the spring, and while the delta T just remains constant. As you can see with these two graphs that display the model and the experimental data, there isn't much difference between the motion. It's just the human error from the tracker that might have made the data different. For the what does it mean questions, well, for the model system, yes, the energy principle is satisfied, and we can see this in the energy graphs since U graph and U spring oscillate in the same periods yet in opposite phases. Overall, we also see that delta E is 0 since no energy is being exchanged between the system and the surroundings. And also, well, analyzing and comparing the periods of oscillation for the x and y positions, we know that the x and y periods are not the same. The y period is smaller slightly than the x period, and this can be due to errors in calculations, and also given that we have the gravity and the spring motion, and the y motion gets reduced as the length of the spring stops to compress and just becomes into equilibrium, and also to the fact that the system is moving in a pendulum.